In section 3.4, we're going to be looking at concavity and the second derivative test. Up until this point, we've only looked at the first derivative test and increasing and decreasing and critical values. Now we're exploring more into some other details of the graph and how those graphs are created. So for concavity, when we want to know if something is concave upward, what we will want to know is when the second derivative is greater than 0. And to help you remember that, I have a very technical way of helping you with that. We're going to draw these little smiley faces. And if your second derivative is positive, like the little eyes, then you have concave upward. If it is concave downward, this is going to be when your second derivative is less than 0. So again, super technical here, this little smiley face. When you have negative, you have concave downward. And I know that seems super lame, but those smiley faces really help me to see the concavity and remember them easier. Now, what's going to be difficult with some of the concavity problems is 1, being clear with your details, and 2, simplification of your derivatives is what's going to catch you. And so let's just jump into an example here in just a minute. We're going to define one more thing before we do that: points of inflection. Well, with your first derivative, when it was equal to 0, that was known as your critical number. When we take and set our second derivative equal to 0, that's going to be our point of inflection, and that's where you have changes in concavity. And again, you can see similar to critical numbers. It's where your f double prime of c is equal to 0 or where it does not exist. And this is going to give us boundaries for our concavity. And so we're going to look here and determine the open intervals on which the graph is concave up or concave down, and determine the points of inflection, if any, on the graph of f of x. And so what I'm going to show you is going to be very similar to what we have been doing with our first derivative test. We're just using it with our second derivative. And so when you see these keywords of finding where it is concave up or concave down, to yourself you need to be thinking, okay, I'm going to have to do the second derivative. And looking at this function, we want to make sure that it is continuous and differentiable, and this one is. It's not going to cause us any issues. And so what we want to do is we want to find the second derivative to get us going, but as you know, you can't just jump to the second derivative. We first have to find the first derivative, and then from its derivative we can find the second. And so my first derivative would be derivative of the top, which is 0, times the bottom, x squared plus 3, minus the top, 6, times the derivative of the bottom, which is just 2x, all over the bottom squared, x squared plus 3. Now I'm going to do my algebra and cleanup. That's why I stressed through chapter 2 to make sure you cleaned up the function. This zeroes out, and so this gives me negative 12x all over, excuse me, I forgot to square it, x squared plus 3 squared. So this is my first derivative, and we want to use that simplified version in order to find our second derivative. And so I'm going to say f double prime of x would be equal to derivative of the top would be negative 12 times the bottom, x squared plus 3 squared, minus the top, negative 12x, times the derivative of the bottom, which would be 2 times x squared plus 3, subtracting 1 from it just gives you a 1, times, don't forget chain rule, the derivative of the inside, 2x, all over the bottom to the fourth. Now typically you're going to leave those denominators raised to powers. You're not going to multiply them out to the fourth power and have a long string of terms, because then if we saw similarities in numerator and denominator, we couldn't get rid of those. Let's clean up the top. That gives me negative 12 times x squared plus 3 squared, and I'm seeing a lot of similarities, so I'm not going to FOIL that out. In the back term, let's see, negative and negative gives me a positive. 2x and 12x is 24x squared times, oh, I have another 2, so let's make that 48, times x squared plus 3, all over x squared plus 3 to the fourth. Now I left it like this and didn't distribute this in yet because I'm noticing a similarity. And I can see this one has an x squared plus 3 and this one has an x squared plus 3, so does the denominator. And so if I factor that out front and I take the smaller of the two, which is the first power, I'm left with negative 12 times x squared plus 3 plus 48x squared all over x squared plus 3 to the 4th. Now, because some of you are very quick to cancel, now we can cancel this with this. So this leaves us with, I'm going to go ahead and distribute this in, negative 12x squared minus 36 plus 48x squared all over x squared plus 3 to the 3rd. And then combine these like terms, so that gives me 36x squared minus 36 over x squared plus 3 squared. In the top, I could factor a 36 out, leaving me with x squared minus 1 over x squared plus 3 squared. And that would be my second derivative. And you're going to see in just a minute why I want to fully simplify this out. A lot of you in your previous exam or homeworks, you would just leave it as a very raw derivative, possibly at this step. You always need to simplify down to lowest terms, because let's see what we can do with that. So just rewriting, if my second derivative is equal to 36 times x squared minus 1 all over x squared plus 3 squared, that's my second derivative. From my second derivative test, if I set this equal to 0, I will be able to find my inflection points. And my inflection points are kind of the barrier between where my concavity is changing. And so that's going to be, if I set this equal to 0, that's only going to happen when my numerator is equal to 0, because fractions don't zero out just by the bottom, only by the top. And so I will say, well, 36 could be 0. Nope, that cannot be true. X squared minus 1 could be 0. So that gives me x to be plus or minus 1. And so I'm going to have inflection points at plus or minus 1. So to state my concavity, you do it similar to your first derivative. You're going to place your inflection points on a number line. You're going to remind yourself that we are plugging into the second derivative. And then you are going to test values to the left and right of that point and pick really easy numbers for you to plug in. If I pick x to be negative 2 and I plug it into my second derivative, that gives me a value of 108 over 343. And I'm just plugging it in right here for x and using my calculator. Since that's a positive value, I'm going to have positive to the left of negative 1. I'm going to pick a value between negative 1 and 1, and I'm going to pick it to be 0. I like to pick easy numbers on myself. This gives me f double prime of 0, plugging it in again into that second derivative, negative 36 over 27. And again, I'm just most concerned about that negative. And so that means between negative 1 and 1, I have negative values. And then I'm going to plug in bigger than 1, let's pick 2. So f double prime of 2 would be equal to 108 over 343. And that is a positive. That's more of what I'm concerned with. So I get positive values over here. So what is this showing me is that using my handy dandy smiley faces, it's going to be concave up here, concave down here, and concave up here. So I could write my intervals that we are concave up from negative infinity to negative 1, union with 1 to infinity. We are concave down between negative 1 and 1. And remember, these are the same as with your first derivative test. They are parentheses because we are not going to have that concavity up or down at the inflection point, just over the other parts of it. And so you can see it's very similar to what we were doing with the first derivative test, but now it's dealing with the concavity and dealing with the upward or downward versus we were dealing with increasing and decreasing in that first derivative test. But it's still setting sum equal to 0 and solving, drawing a number line, and checking values on both sides of it. That would be the similarities. Now, concavity comes in handy in some other ways. If we know that we can use our first derivative test in order to find critical numbers, then using the concavity, we can even jump steps and figure out local minimums and maximums. And so this is where the second derivative test comes in handy in finding local min and maxes. Consider this. If we test critical numbers, because we know something's happening at those ones as we have defined as critical, in the second derivative, then that's going to tell me by the concavity at that critical number if it was a max or min. And so if the concavity is positive or concave up at the critical number, well, let's think about this. If it's concave up at the critical number, then that means that point is a minimum or a local minimum, because I haven't compared it to all of the function. If that is concave down, think about your smiley face, then that would create a maximum, or actually a local maximum, at that critical number. If it's equal to 0, then we can't use this shortcut. The test fails, and you need to go back to your first derivative test and look at your intervals and your values of increasing, decreasing. So what the second derivative test is, based off the concavity, we can state if something's a max or min without having to go through that whole testing of the intervals. We just have to take critical numbers and then plug them into our second derivative. So this example says, find the local extrema for f of x using the second derivative test. Okay, so first thing I'm going to have to do is I'm going to have to find my derivative. That would give me negative 15x to the fourth plus 15x squared. Okay, I still have to use my first derivative and say it equal to 0 in order to find the critical numbers that I'm going to test. So I'm going to factor out a negative 15x squared. That leaves me with x squared minus 1 equal to 0. And so that means negative 15x squared equal to 0 gives me x to be 0. X squared minus 1 to be 0 gives me x squared equal to 1. So x would be equal to plus or minus 1. So you still have to use your first derivative test because these are your critical numbers, and we want to figure out what's going on with these critical numbers. Now we're going to test it with our second derivative. So I'm going to go ahead and find my second derivative, and that would be negative 60x cubed plus 30x. And I'm going to take each of my critical numbers and plug them into my second derivative. So I'm going to say f double prime of 0. That gives me negative 60 times 0 cubed plus 30 times 0, giving me a value of 0. Now the problem with this one is my test is going to fail at this value, so I'm going to have to revert back to my first derivative test. But let's check it for the other two. F double prime of 1 would be equal to negative 60 times 1 cubed plus 30 times 1, and so that gives me a value of negative 30. Well, that's negative, so that tells me I'm going to have a max at x equal to 1 just by that second derivative test. F double prime at, negative 1 would be equal to negative 60 times negative 1 cubed plus 30 times negative 1, resulting in a value of positive 30. So we're looking at a smiley face here, and so I'm going to have a minimum at x equal to negative 1. Now, we know what's going on at negative 1 and 1, but because this asks us to find all the local extrema and that first derivative test fails on 0, I'm going to have to go do some first derivative work here. So I'm going to draw my number line. Let me move right back over to red. I'm going to go ahead and draw my number line. And you know what? I'm just going to check at what's going on at 0, but I am going to have the boundaries of negative 1 and 1 because I don't want to pick numbers too large. If I pick, say, x to be negative 1/2, f prime of negative 1/2 is equal to 45 over 16, so I get a positive value here. Again, remember, we're just trying to find what happened at 0 because our second derivative test doesn't work. I'm going to do x equal to 1/2. And so plugging in 1/2 into that function gives me 45 over 16, so positive again. So therefore, from using this little first derivative test at 0, we know that x equals 0 is not a minimum or maximum. It looks like it's just changing in speed of its increasing or decreasing. But look back at that second derivative. Wasn't that really great that I didn't have to check all these different values like we did with 0? We were able just to check into our second derivative based off our smiley faces and determine a minimum or maximum. But you could see the value of 0 fell into that place of, oh, the test fails. And so I hope this helps you to see how that second derivative can work, how your concavity is working, and let me know if you have any questions along the way.